Hello, ladies and gentlemen. Today we're going to look at the linear regression. Uh, we're going to talk a bit about linear regression. So then we have the next video, which we talk much more about this model. But let's start. This is a short introduction about the linear regressions. But if you have questions, if you have such things to ask, you can just put them in the comments. So my name is Abednego Samo. So I'm student right now in master degree at African Institute for Mathematical at in Rwanda, Kigali. So then, these the quick introductions about the linear regressions. So then we can just say so quickly that linear regression is a statistical method used to model a relationship between um, dependent variables, which is y, and then the independent variables, which is x. So then if you want to do the linear regressions, we have to make sure that um, the output um, is numerical, and this is really important. Is the first thing we will talk about the assumption of linear regressions, but we have to make sure that the outputs are numerical. So then, in this case, we can talk about the linear regressions and the input. Is it output? Let's say the dependent variables. Dependent variable is numerical, and the independent variables are also numericals. Then it's assumed that the relationship is linear, meaning that y can be expressed as linear functions of x plus an error terms, mean that we have some kind of relations which can be expressed by linear relation between those variable y and x. So these are the assumption of our linear regressions. So first of all, we assume that we have the linearity relation between x and y. The second thing is independence. The observations are independent, meaning that if you have the first observation, the second observation does depend on the first observation. So each line of our observations are all independent. So this is the third assumption is constant variance of residual. So then the residual should have a constant variance. So then the variance of residual we see it at the end of these presentations how to check these assumptions on our model. So then to help us to validate the model if this will be useful or not. So then we have the fourth assumption, which is residual follow a normal distributions. So then our residual should follow the normal distributions, and it's a bit in link with the third assumptions. And then the fifth one is no multicollinearity. So the meaning that the predictors are not highly correlated in my X. If I have several variables in my X, like I have X, several columns in my X, this means that each column and the two columns are not saying the same things about the my variable Y. I mean, there is no these variable are not correlated. We can check these correlations by plotting or by checking the um, correlations matrix of the of x. So then we can see these columns, these predictors which are strongly correlated. So then in this case we can check if we should remove or take decisions about that. So then we see them in the next another video, but this is just a short introduction about linear regression. So then we will use the builds mtcals. We can check this data in helps. You can check it online. So then we have much more information. But if you need me to put much more information about this, just put them in comments. So this is data set already in R, because we are going to use R to program these models. And then if you need Python's experience in Python, you can just ask them in comments. So then we do it them in comments in Python. So here's a quick look at the data sets. This is how we import the data set, like data mtcals, and then we check the head. We have here our x. Let's say we have these variables here. There are several variables that we can check, but we are not the we as far as we are concerned here is just to do a simple linear regression, like uh, just our y and one column of x. Mean that we have two columns, we just choose two columns, one here for y and the second one for x, then see the relation between how x explain the our y variables. So then at the next step now we will see what will be our y and then what is our x. So then we're going to model mpg, which is mil per gallon, as function of wt. Wt is weight. So then we check the relation between these variables and the weights, this one. So we choose this column and this column. So the first thing is just that you can just notice that here I have already my, you see that y, this is represent y. So then you can see that they are all numerics, they are real, and then we have this one too. As I said earlier, we are just building um, a simple linear regressions, meaning that I just have my y and I have one x, so then two columns. Maybe in the next video we really explain, because this one is just a view to get interest in our model, how work linear regressions. Just a quick introduction. So then we come back and talk deeply about the theoretical of linear regressions, how do they build them, how these things are working, and everything, the statistic behind this model. So then we come back in the next video, we explain those things. Just follow this, which will give you the idea about how this model work. So then, as I said earlier, we're going to model mpg, mils per gallon, as function of the wt, which is weight. So then let's quickly check the relationship between we plot we let's quickly do this. I'm creating a new chunk, okay, to see what is the relation between the weights and mpg. As you can see, I just plot the weights in function. Um, Let me check these things quickly. I just plot the mpg in function of weight. So then you can see, yeah, mpg in function of weight. You can see that we have such kind of relation, linear relation. So then we can just put a line through somewhere here, which can give us the, it's possible, is that what I'm saying? It's possible to find a line which will reduce as much as possible the errors of predictions. So then, let's go back. As we saw these things, now we try to build a model. This is how to build a model. We build a simple model and with LM, and then we build MPG function of weight. Our data is empty car we imported before. Yeah. So then let's build a model. After building the model, we look at the summary of the model. What is the output? Okay, this is the output. You can see here we have information about residual. We talk about this one later, but let's focus on these coefficients. So then we see how this weight explain the MPG, our Y, which is MPG. Okay, let's look at this one, and you will look at the estimate. You see 37.28. What does this mean? This coefficient means that when the weight is zero, when we have no weight, so then initially the MPG, the value of MPG is 37.28. And then let's look at this p-value, because p-value will help us to appreciate this. If this variable is this coefficient is significantly statistically significant, meaning that it should be statistically zero or not. Okay, then here we have that the p-value is really less than 0.05, meaning that this is strongly significant statistically talking. Then, okay, look at the weight. This is really important again. We have this estimate. Okay, the coefficient of weight is minus 5.3445. What does this mean? It means that when the weight increase by 1, then MPG decrease by 5.445. You can also interpret it like when the weight increase by 1, then the MPG increase by minus 5.3445. Okay, we have this coefficient, but let's see if this coefficient is really statistically significant. So then we just go back quickly to look at its p-value. Okay, we can explain what does this p-value coming, where is this p-value coming from, and then the t-value also. So then we have the standard deviation, error. These things are all their interpretation. But let's say keep it like we said, just a quick introduction about the linear regression. Then coming here, we are interested in seeing if this value, if this coefficient of weight is really significant. We can also all notice it here that this value of p, the value of p value is really less than 0.05, which is really significant. So then we can say that there is a relation, this relation and the weight explained um, by this regression, the MPG. But we can also see here that the p-value of the model is less than 0.05. So then we can say that the model is significant, statistically significant. So then we can use the model. But calm down. This is not the end. We should check the assumptions talk we listed above. So then we go and quickly to check the assumptions as I said earlier. So then visualizing, but before checking the assumption, let's plot the line, okay, suggested by the model. We plot the line and visualize how this line go through. So you can notice it here. This is our model. Okay, meaning that if I want to predict this point here now, I just need to do the projection here, and with this line, we all notice that there is errors. You see variations, but okay, this is the line suggested by the model. Okay, at the end, we will check the assumptions on the model. I'm coming in. Let me put this thing here. So then how do we check the assumptions of the model? We can just come here and do the let me put these things here. Okay, this is per flow. Okay, this is per. Okay, okay, m flow, mf row, mf row equals to c. So then I will precise if I want how many columns, because I'm going to plot this assumption. There's four assumptions, and then we're going to do the interpretations. So then let me put 2 2. This will give the matrix of four coefficients. Then I will do the plot. I will plot the simple. I'll plot the simple model. Assume that we not made mistakes, guys. Okay, the first one is working. But simple model not found. How do we call the model? Okay, model simple. That how we call it. Model simple. So then this we build. Okay, you see. So this is the interpretations of the plots we have there. So the first plot show the residues versus values, and then the objective is to check the homoscedasticity, and then if the points are well distributed, if the points are distributed randomly um, around the horizontal line, this means that the model is good. But here we can notice the a curve. Okay, this is not um, really things like linear like this. Then it is non-linear. So this can tell us that the relations between the variables is not perfectly linear. Okay, so then we cannot use 100% the linear relation to express. So then we can maybe to express the relation between our y here and the x. So then that's what we can conclude from the first. And the second one show us the QQ plots. The objective is to check the normality of residues. If the residues are normal, then we can see that if the points follow a line, a straight line. So this suggests that the residues follow a normal distributions. Then in this case, we just notice that are some uh, anomaly in the tail. So this can show us that the problem of normality of the residues. So we can notice again the presence of aberrant values. The second one is to check the homoscedasticity if the variance is constant, the residue size variance is constant. So then we can say yes if these points are well distributed uniformly around the horizontal line. So then here there is some, you see, uh, some uh, I can say, let how to check it now. You see there is some like curve, something like that, which is not respect the first thing I said. So then in this case we can just say that the it is possible, okay, it possible be to have to not have the homoscedasticity. So then the fourth one show the residues versus leverage. So then the objective is to identify the influent points. Then the interpretation is this one. We have the influent points. So then in this case, we can check. You can see that the points are really far from the really far, and then this has the big effect on the model. So then then in this case, we cannot be really sure that we can. You see, as I said earlier, the model is really significant, statistical significant, but while checking the assumptions, we are just seeing that there are such things that are not really okay. Yeah. But anyway, the QQ residual, you see, but in this case, we can accept, but the first plot, you see, so then we can try, in conclusion we can try to uh, find another best model, okay, which can do better than this one. Okay, so then this is the end, and then we are going to wait for the next video. Thank you very much. And this how to check the assumptions. Those other assumptions I didn't talk about, we suggest that this one are already good. So thank you very much for watching the videos. See you.